Welcome to Study Loop.
So we have a parallel plate capacitor with charges plus Q0 and minus Q0. And they're joined by this dielectric with a known dielectric constant K, resistivity rho, and separation D with area A. Now the plates of the capacitor discharge, which means that there's going to be a current flowing through the plates. And because there's a current, we can calculate the current density. So that's part A. And then we have to show that the charging current density is equal to the negative of the displacement current density. So first of all, we're looking for a current. Ohm's law is probably a good place to start. So we know that current is equal to voltage divided by resistance. And then what's the voltage of a capacitor? Well, we also have that the voltage across the capacitor is the charge across the capacitor divided by the capacitance. Okay, so Q equals VC. And then we also know the capacitance of a parallel plate capacitor. That's K epsilon naught A over D. So we have all these formulas. And so let's just start substituting them into each other. So the current is, so let's substitute the voltage into here. So this is going to be the charge divided by RC. And then the capacitance is going to give us D upstairs, because C is downstairs, times the charge divided by K epsilon naught RA. So now we should find the resistance. So what's the resistance in question? Well, for that, we can use the formula for the resistance of a cylindrical type object or an object with a known cross-sectional area. It doesn't necessarily have to be a cylinder. So the resistance is the resistivity rho times the length, which is D, right? Just that length of the dielectric, divided by the area, and that's A. So now we can put this in there. So the current, so you can see that the A and the D are going to cancel, right? There's a D over A, and here's a D over A. So the D over A's are going to cancel. And what we end up with is just D times Q over T divided by K epsilon naught rho. So there's an expression for the current as a function of time in terms of the charge. Now we can create a differential equation by using the fact that the rate of change of charge is current. So the definition of current is the rate of change of charge, but in this case, it's actually going to be minus dq dt. So it's negative because essentially the charge is decreasing. So that's why we have to put this negative sign in there. So the differential equation we have is dq dt equals d. Now I realize this d there is confusing, so I'm going to put these, I'm going to write it like this: d over k epsilon naught rho times q of t. So this d is not like a differential d, it's this distance d. Okay, so that's a differential equation, and the initial condition is that q at 0 is q naught, right? That's the initial charge up there. So this is solvable by just integrating both sides. So it's going to be an exponential. And what you find is that q of t is q naught times e to the negative t over k epsilon naught rho. So there's the expression for the charge. And then to get the current, we just go back and take the derivative. So the current is minus dq dt, which is q0 over k epsilon naught rho times e to the minus t over k epsilon naught rho. And there's the charge, or excuse me, there's the current. And now finally, the last step is to just compute the density. So now this is straightforward because we just divide that by the area. So the final answer is we have k epsilon naught rho a downstairs, q naught upstairs, and then e to the minus t over k epsilon naught rho. So there's the conduction current density. Now, how about the displacement current density? So for the displacement current density, we can just go back to the definition. So it's epsilon times dE dt. Epsilon is k times epsilon 0 by definition, times dE dt. And then we can use a formula for the electric field inside a capacitor. So remember that there's a formula for that. The electric field inside a capacitor is the charge divided by k epsilon naught a. All right, so that's what we're going to use in here. And then all of this stuff is a constant, right? So I'll substitute it in first. So this is the derivative of q of t over k epsilon naught a. Okay, so the k epsilon naughts cancel out and a is a constant. So this just becomes 1 over a times dq dt. But then dq dt is minus I over a, which is minus the conduction current. And that's the full solution to the problem.